All right, well, welcome in and happy Friday, everyone. I hope that the quiz went well for you. Just a reminder that our midterm exam is next week. So start thinking about how you're going to divvy up your time and make sure to dedicate some time studying for the midterm. Over the weekend would be good, or certainly next week. So yeah, today we're going to talk about 16.2, which is all about line integrals. And I wanted to start with this here because it actually surprisingly has something to do with our class here today. So from 12.3, we talked about the dot product quite a bit. So u dot v here got us a couple of vectors. And my question is, in each case, can we recall, right, when are you going to have a positive dot product, when will you have a negative dot product, and when will you have a zero dot product? So I guess the zero dot product is, I think, comes fairly quickly. I think most people remember that. Can anyone tell me A, B, C, D, which one of these is going to be zero? Yeah, C, right? So when you have perpendicular vectors, and I tried my best to make them perpendicular here, the intent was certainly to be perpendicular, that u dot v is equal to 0. So that's the zero case here. Okay, so besides that, none of the other ones really look perpendicular. The rest of them, it looks like, well, A and B and C, U is on the left and V is on the right. For D, V is on the left and U is on the right. So we need to remember that really the order doesn't matter for dot products. It does for cross products, but for dot products, not so much. So it doesn't really matter the order here. And can anyone give me a compelling reason for A? Is this positive or negative and why? Anyone remember? Yeah, here.
Is acute, and the value of the dot product is reliant on cosine of theta.
Good. So the claim was that the angle is acute between these two. So if we were to write this out, right, one of the definitions for the dot product here, or a theorem for the dot product, notice that this is reliant on cosine of the angle between these vectors. So certainly the magnitudes, right, these are going to be, again, we know how to calculate out a magnitude of a vector. There's a square root and a bunch of squares added together. So this is going to be positive. This is going to be positive. And then you have an angle that's less than 90 degrees, and you throw that into cosine, then this is going to be positive here as well. So you have positive times positive times positive, and so this one's going to be positive overall. And for B, we have an obtuse angle. So as you would probably guess here, when you go and you throw in an obtuse angle into this, and remember how cosine acts, right? You're going to have positive times positive and cosine of 3 pi over 4, 5 pi over 6, any of these obtuse angles, right, you get a negative. And so overall, this is going to be negative. And we already talked about how the order doesn't really matter. So this one here is going to be positive. So my claim is this is going to help us kind of visualize and understand some of what I talked about last time, but especially as we move forward and do line integrals over vector fields, this ends up being quite important. So that's kind of why I wanted to do this as a little bit of a warm-up before we get into the stuff for today. With that, let's go ahead and transition, and I'd like to review the pre-class video really quick. So line integrals, here's the stuff that we talked about before class. And we go into, well, I guess for many of these line integrals, you're going to have a parametrized curve. And so a lot of the stuff that we did back in 13.1 is going to come kind of back around for us, and we need to parametrize a lot of curves. One of the common parameterizations that we had was for line segments, right? And so I just reminded, actually this came up in 12.5, but a formula for parametrizing line segments comes up quite a bit. And so it's good to have that kind of at our fingertips. And then I mentioned we're going to have this integrating along a curve. So integrating as we take tiny steps. So these tiny steps are going to be my ds's. So we calculated out this ds. However, when we actually go to evaluate out these integrals, they're going to rely on time. So we need to relate together, how does a tiny step relate to a tiny increase in time? And so we need a relation to trade in ds's, tiny steps, versus dt's, tiny changes in time. And so this is exactly the formula right here. And you can see it does rely on the arc length. with this, well, a little bit of a preview of what's to come in chapter 15, but it turns out the integral of 1 turns out to be a very kind of fruitful endeavor, right? There's a lot of kind of geometric meaning to integrating 1. And so in this case, actually, if you integrate 1 ds, now with this new, taking tiny steps with respect to s here, you get the arc length. And as you'll see in chapter 15, integrating 1 with a triple integral will give us volume. Integrating 1 with a double integral will give us area. And you can even do this in curves in space, in surfaces in space as well. But that's all stuff to come still. So a few more definitions here, and then ultimately we get to an example, right? And so the example is we're adding something up along a curve. In this case, we're imagining that we're some whale that's swimming, throughout the ocean or whatnot. And the thing that we're adding up is plankton, right? So they basically just, again, gather these plankton as they go. And so we have some plankton density function, and we want to add that up and ask how many plankton in total did we eat as we went along this portion of the curve, right? And so it turns out that the answer was 4 in this case. But this is kind of some real world meaning to what we're calculating. So we're no longer calculating out in length of a curve necessarily. I mean, we can do that. But if you're integrating some other function, right, you're adding something up along the curve that's maybe not just length. So in this case, we added up how many plankton we're eating along the curve. Question, yes?
What is like a
Yeah, so again, the question is, what are you summing up as you travel along the curve? You can sum up all sorts of things. So if you switch out this f here, you can really sum up just about anything along the curve. And especially if you give it to a computer or something, right? Really the functions can be much more complicated in that case. So the common one that, of course, we've done in the past is just sum up the length, right? As we take tiny steps, basically, you take one tiny step, 1 ds, another ds, and we add that up all along the curve, and we can get arc length. But this is just saying that we can add up other functions along the curve. And so this was a little bit of a silly one of eating plankton. So we're adding up the number of plankton. But as you can see in our new stuff for today, we can add up other things. So for instance, we have a height function. And as we travel along this curve, we can add up the heights. And this is going to give us the area under the curve in a 3-dimensional sense. We can also add up other density functions. So besides just plankton, you can add up, well, probably a more nice one is going to be mass density, right? And so if you have some mass density function, in particular, maybe we have some spring, then you can answer the question, how heavy is the spring overall with just the density function? So these are some examples of what we're going to be able to calculate out. And then we're going to be getting into the line integrals with vector fields. Question, yeah. So yeah, in this case here, there is no dot product because we don't have any vectors yet, right? So yeah, once we do line integrals with vector fields, then there'll end up being a dot product, but we need to still kind of develop that. All right, well then, why don't we do a few examples before we get into the line integrals with vector fields. So starting off here, we have a portion of a wall, and I would like to figure out how many bricks, right? If I wanted to build this portion of a wall, how many bricks should I bring with me, sort of deal. So we're going to calculate out the cross-sectional area, and then apparently each brick has a cross-sectional area of 100 centimeters, fairly large bricks. And then how much do we need in order to build this portion of the wall? So the thing that we are adding up is going to be our height over this curve. So here's the setup. I can go ahead and put in my height function. So xy squared ds. And now when we integrate this, we're going to try to switch everything over to t's. So we have some parameterized curve here that tells us how we're moving. And so, of course, with the parameterization, we have an x component and a y component. So we're going to go ahead and start swapping these things in. So instead of x, I'm going to put 2 sine t. Instead of y, oops, I'm going to put 2 cosine t. Notice it's supposed to be y squared, so I need to square that. Now that we've swapped it into t's, our parameterizations, if they don't go on forever, they have very specific starting and ending points. Those nicely become our bounds for our integral. So we're going to integrate this from 0 to pi. But then the only question left is, well, I need to swap in this ds for so many dt's, right? And so there's an exchange rate. And again, in the pre-class video, it was brought up that ds is going to be equal to, and you have the square root of, let's do dx dt squared plus dy dt squared. So again, it's going to be this bit from the arc length. So this should look familiar from our arc length formula there. That's the thing that we used to integrate if we were in 3 dimensions that had z's. But in this case, our parameterization just has x's and y's. So we need to swap that in, but this is the most common mistake that I see when folks are doing line integrals, is that they're going along, doing everything fairly correct, and then they just say, ds, let's swap that out and put a dt. Or they just stop writing them all together, right? They just don't write the ds or the dt, so they don't face their issue here. But again, ds is not the same thing as dt. You have an exchange rate here. It depends on how fast you're going. A tiny increment of time is not necessarily equal to a tiny increment in space, right? ds, a tiny step along this curve. So it really depends on how fast you're going. And so we need this stuff with the square root. We're gonna have to square some things, add those together, and then we can have our dt. So let's calculate out. And we need to take derivatives of our parameterization with respect to t. So I'm going to go ahead and basically calculate out over here my r prime. So the derivative of sine is going to be cosine in the x component. In the y component, I have to take a derivative of cosine. That's going to be negative sine. So if I calculate out the magnitude of this, aka I'm going to square these things, add them together, put them under a square root, what I'm going to get 4 cosine squared t, and then, sorry, I don't need to square it yet. I'm about to square it according to what I've written here previously. So let me back up here and just input these. So what's 2 cosine t and negative 2 sine t. So there's my derivatives. Now let's go ahead and square these and do all that. So I'm going to have what? 4 cosine squared plus 4 sine squared. If I factor out my 4, I'm going to get cosine squared plus sine squared. That's equivalent to 1. So I'm going to have the square root of 4 times 1. The square root of 4 is 2. So ultimately, this is going to be 16. All right, now I still need to integrate my sine t cosine squared t. This is going to be a small u substitution. So if I let u be equal to cosine of t, then du is going to be equal to negative sine of t dt. So now this is just going to be the integral of what? Negative u squared du here. So again, I have 2 cosines being multiplied together, so that's the u squared. And then I only have a positive sign here, so really I need to move that negative sign off to the other side, so it's negative du. That's where the negative sign came from. So let's see, I'm going to have negative 16/3 u cubed. So u again was cosine. And this is what I need to evaluate from 0 to pi. Again, those were t values, so it's best to swap back in your t's. So when I plug in pi into cosine, I'm going to get negative 1. When I cube it, I'll get negative 1. And so I'll have negative 1 times negative 16/3. That's going to be positive 16/3. From that, I need to subtract away negative 16/3. And then cosine of 0 is supposed to be 1. And again, I need to cube that. That's still 1. Multiply it by the 16/3. That's going to be 16/3. All right, so this is how many, well, let's see. This was in meters. We're going to assume that everything here is in meters. So this is, I guess, square meters. And I need to figure out how many bricks. So we got a tiny bit of dimensional analysis here. So what I have that each brick is 100 square centimeters, right? So let's see what I have that, what 100 centimeters is 1 meter. I need to do that twice because it's meters squared. So 100 centimeters is 1 meter. So now I can cancel out my meter squared. And then the last bit here that I'm running out of room for is that what 1 brick is the same thing as 100 square centimeters. So I can cancel one of the 100s and both of my centimeters here to transform units into bricks. So it looks like what I need 3,200 divided by 3 bricks, which is approximately 1,067 bricks. Typically in our math class, we don't have so much of these transforming of units, but since I had a little bit more of a real world problem here, I decided to include this once. Of course, if you're, the contractor hired to build this portion of the wall, you should always add 10%, right? So buy, an extra 100 bricks. Any questions on this one here? Yes.
Like the 8 sine t cosine t, like that step to the next step.
Yeah, so there was a couple of things that I did here, and I just kind of talked through it. So I apologize for not writing down as much as maybe I should have. But the first thing is that I needed to simplify this bit under the square root, right? So I factored out the 4, and then I had cosine squared plus sine squared, that's 1. So this all became basically the square root of 4. Oops. So this was the square root of 4 times, again, the cosine squared plus sine squared was 1. So the square root of 4 is going to be the 2. I still have this 8 out in front and this other stuff. So the square root of 4 being 2 times the 8 give me the 16 in total. And then the question was, back from our calculus 1 days really, how do I evaluate out this integral of sine t cosine squared t? And I said that a u substitution should work quite well for that. So then we let u be equal to cosine and found that our du was hanging around, which is always quite nice for the u substitutions. And so we got a relatively nice u integral once we substituted all that stuff in. Good, you guys ready for another one? All right, let's do it. So here I have, again, some density function and some curve in space. And now the question is, right, how heavy is the spring in total? So when I integrate this density over our curve, this is going to give us the total mass. So in this case, we have what, 10 minus x minus y. This is the density function. And I'd like to add that up along my curve and see how heavy this is in total. So if I go ahead and, like I mentioned before, right, anytime we have a parameterization, we have an x and a y. This one is in space, so we have a z as well. And so I'd like to go ahead and start converting all of my stuff into t's. So I'm going to have 10 minus x minus y. And again, don't forget to transform your ds into dt's. So you're going to need to have the square root of, and let's go ahead and take the derivative of these. So the derivative of 3 sine is going to be 3 cosine. I'll square that. The derivative of y is going to be negative 3 sine. Square that. And the derivative of z is going to be 4. Square that. So this is the correct transformation from ds into dt. We need to take the derivative of our parameterization and then find the magnitude of that. Now that we've swapped this into t's, we can also set up our t bounds, right? So our t bounds are going to be from 0 to 8 pi in this case. All right, now we're going to go ahead and try to simplify the square root stuff as much as possible. So let's see, I'm going to have 9 cosine squared plus 9 sine squared. And so I'm going to factor out the 9 from both of those, plus 16. So again, cosine squared plus sine squared nicely is 1. So this is going to be 9 plus 16. That's going to be the square root of 25 in total. So it looks like we're going to have the square root of 25 as 5. So I'm going to go ahead and put that 5 up here in front. And now we are ready to integrate. So let's see, the 5's along for the ride. When I integrate 10, I'm going to get, what, 10t? When I integrate when I integrate sine first, I'm going to get negative cosine. And when I integrate cosine, I get sine. This is what I need to evaluate from 0 to 8 pi. So why don't we go ahead through here. Again, we're going to have 5 times a whole bunch of stuff. I'll have 10 and what we have 8 pi minus 0, I suppose, if I just evaluate these term by term, plus 3. And cosine of 8 pi is going to be, what, 1, minus cosine of 0, also 1. So this part just goes away. Now, sine of 8 pi is 0, and sine of 0 is 0. So these pieces just go away here. And let's see. So my final answer is going to be this 5 times the 10 times the 8 pi. So what, 400 pi. And the units here will be in grams. So again, we're kind of imagining that our original function here had units of grams per centimeter, and then we integrated, we added up, right, and our ds will have units of centimeters, right, a tiny step along this, staying with the same units and all that sort of stuff. So grams per centimeter will cancel with centimeters a little bit, and that's you get just grams. Question, yes?
Can you always do that? Just like you input like those values into t, like 8 pi and 0. Can you always just do like 8 pi minus 0?
Yeah, I quite often, so the question was in this last bit here, I evaluated these out term by term rather than plugging in 8 pi into everything and then subtracting away 0 for everything. And yeah, I quite often do this when evaluating out integrals, just because I find it's a little bit simpler, and especially when you have like fractions and stuff like this, like if there was, I don't know, maybe like a 1/5 out in front, it kind of just keeps all the common denominator stuff together. So I find it like a convenience thing. You don't have to do this, but you certainly can. Yeah, I mean, you still have to make sure you plug them into the function, though, right? So, I mean, you have to take that 8 pi and really plug it into the cosine and take the 0 and plug it into the cosine. That's a common mistake that I sometimes see if people try to do this too fast. But yeah, make sure to plug it into the function. But so long as you're doing that, yeah, it works. Good. Any other questions? All right. Well, that concludes our line integrals with scalar functions. We now need to swap over and start talking about line integrals with vector fields. So, I mean, technically, when we have a line integral with a vector field, it is a line integral with a scalar function. It's just the scalar function is a very particular, almost confusing. Like, why would you choose this scalar function? But it's going to be you have a vector field and you dot product with the unit tangent vector. So this thing right here, right? We saw this back in what, 13.2. This was the unit tangent vector here. Now, if you were to evaluate out the line integral, right, just as is, remember you need to swap out instead of your ds, you need to exchange that for some number of dt's, right? So you can see that you get this extra magnitude of your derivative there. And so there are multiple ways that you can write this. And so like I mentioned here, there's probably like 5 ways or so that we can express line integrals with vector fields. And the big thing for this is I'd like to kind of spell them all out and just make sure that if you see any one of these, you should realize that it's a line integral with a vector field. So the first is going to be maybe f dot t ds. So again, we have our f, our vector field here. We have our unit tangent vector, that's the t. And then again, all of this stuff right here was just the same thing as ds. Tiny step is, right, that was our transformation into how many ds's is worth a dt. Now, my favorite one to use looks like this. So it's the integral, oops, switch back to the pen. The integral of f of r of t dot r prime of t dt. I consider this basically the working definition. Whenever I see any of the 5 ways that you can express a line integral with a vector field, I pretty much always transform them into this one here. So no matter which of the 5 they give me, I pretty much always transform it into this one here. So again, for this one here, it's basically just I've allowed my r prime of t's, these magnitudes of r prime of t's to cancel, right? And so that's why this formula is true. So a perfectly reasonable thing to do. Shorthand for this would be f dot dr. So this kind of comes from the old Leibniz notation, right? Where r prime of t is equal to dr dt. And so if you multiply this by dt on both sides, r prime of t dt would be equal to dr dt. And it's kind of like that these things cancel. The dt's. And so that's why it's kind of the dr notation is also fine. So this is again some shorthand. If you have names for your vector field components, right? So if I say that my first component is P and my second component is Q, then I could actually evaluate out this dot product a little bit farther. And so I could write, for instance, that this is the integral of P dx plus Q dy. So this is another way to express the line integral. And again, this is if you have a 2-dimensional vector field. If you had a 3-dimensional vector field that has an x and a y and a z component, then in this case, it would be P dx plus Q dy plus R dz. So these are the 5 different notations, 5 different ways that you can say, evaluate out a line integral. And again, pretty much no matter which one I see, I always just turn it into my working definition. And so we'll kind of illustrate this here in just a second. But before we get to that, right, I mentioned here, besides just a great way to torture math students, what is this really used for? Why make this definition here? And the answer is the work. So work done by a vector field. How much work does a vector field do? How much work does a gravity field do or electromagnetism field do? Anything like this. And so if we have F being a force field, then the work done by that field over some curve and moving some particle here is going to be the integral of F dot T ds. This is a theorem, so I'd like to give you kind of an idea of a proof for this. We've seen work once before in our class in 12.3. We talked about how work was force dot displacement in 12.3. So this is one of our applications for the dot product. So in this case, right, if you want to know how much work a force field is doing at a particular point, as moving something along a curve, maybe I'll draw the picture sooner rather than later here. So let's suppose that I'm traveling from A to B along this curve, and we have some interesting force field. So again, it's a vector field, so everywhere in space or in this plane or whatnot, we have some vectors. Of course, we're most interested in the ones that are, basically on top of this curve here. Stuff like this, maybe. And so if we're moving particles along this curve, then the displacement needs to be along the curve. And at each point on the curve, we're going to move in the direction of the tangent vector. So hence the t's. So that's the work done at a point. So if I draw in my tangent vectors here, maybe down here where this vector field vector crosses, the tangent vector would be in this direction. There's my tangent. For this one, the tangent vector, again, tangent with a curve, is going to be along this way. Here, my tangent vector is going to be, again, tangent to the curve, something like this. And here, again, tangent to the curve, so in the direction that the curve's heading, something like this. So there's all my t's. And again, these are various vector field vectors. So these are various f's, depending on what the x and the y value is. So that, again, is the work at a point. If I want to get the work done over the entire curve, well, then I need to add up the work done at each one of these points. So the way that we add things up in math is, of course, with an integral. So we're going to integrate this over our curve. And if I add up all of these values over the curve, right, then this will give me the total amount of work done. This is the bet here that kind of relates to what we did before class. Notice that if your vector field is largely heading in the same direction as your tangent vector, when you take that dot product, f dot t, this is going to be a nice positive number. And so again, we have an acute angle here. They're largely headed in the same direction. So again, we're going to have positive when we take our dot product. Here, still positive, here, still positive. And so we're going to be adding up a bunch of positives. And so the overall result will be positive. At the end of class last time, I told you guys, if the vector field is helping push particles along the curve, the overall result will be positive. And it's largely just because of this dot product here. It's because the dot product, if it's helping push these along the curve, then it means that the angle between those vectors is acute. It's less than 90 degrees. If it's kind of, rather be going, back towards A or something like this, if the vector field is pushing the other way, right, then it's largely hurting, and that's why you would get a negative, because you'd have an obtuse angle. So overall, when you added those up, you would get a negative. So that's kind of why, again, last time I told you guys that if we're helping, I guess helping was this one right here. If we're helping push particles along the curve, our line integral will be positive. If we're hurting, it really doesn't want particles going from P to Q in this case, we'd get a negative line integral. And if it's a wash, right, if it's kind of half helping, half hurting, or if it's just kind of pointing in directions that, again, not really helping going from P to Q or hurting overall, then we get 0. So that's just that bit there, kind of why mathematically this is telling us something about helping and hurting particles traveling along the curve. Any questions about this before we start doing some problems? All right, well then, I've given us a picture of a force field. And I'd like to first determine, just kind of, again, using the picture, and this is a good conceptual question. I can imagine a true-false question like this on a quiz or an exam or what have you. Just determine if the work in moving the particle along the curve is positive or negative. Again, just using the picture. So I don't have to tell you what the equation is or anything like that. It looks like the curve that we're traveling along is a quarter circle starting off at 0, 1, so up here, and ending at 1, 0. Down here. So if it's a quarter circle, it's going to look something like this. And I could try to guess what my vector field looks like close to each one of, at least close to a sample of points here along this curve. So I can see that there's one that's very close here that's just barely pointing down and to the right. It's a small vector. A little bit farther over here, again, it's pointing down and to the right, a little bit larger this time. This one's basically right on top of it. That's nice. Maybe over here, this is pointing quite a ways to the right, maybe not that much, just a little bit down. And then maybe over here, if I had to guess, right, maybe the vector would look something like this if I had to draw an extra vector field vector that was right on top of our line. Now let's draw some tangent vectors, right? So my tangent vectors, if I'm traveling, again, from 0, 1 to 1, 0, so I'm traveling in this clockwise direction here. Let's see, I'd have my tangent vector would be pointing in this direction. Then again, along the same direction of our curve here. So something like this. And all of these look like they're acute angles between my vector field vectors and my tangent vectors. So I think we're going to have positive, 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 positive. So if I add up a bunch of positives, overall, my result will be positive. So essentially what we found out is F dot T, in our case, is some positive. I don't know what it is yet without specific values, but I found that's positive. So when we add up a bunch of positives, again, we're supposed to be integrating F dot T, that overall, adding up a bunch of positives should give us a positive result. So this is the intuition. And now I'd like to do the same problem again, but from an algebraic standpoint, right? Instead of being able to visualize this, I'm just going to evaluate the work done by this force field. So this is the equation that helped me generate this picture here. I'm moving a particle along this quarter circle from 0, 1 to 1, 0. Oh, sorry, question. Sorry, one more time. Does the length of the vector?
I took that on.
Yes. So, I mean, when you evaluate out a dot product, right, of like u dot v, like we did in the warm up for today's class, right? Part of that is the length of u, the length of v, and then the cosine of the angle between them, right? So if you have longer vectors, of course, this will influence it, right? However, with a unit tangent vector, right, this capital T, the length of that one is always 1. So these green ones that I tried to draw here that were meant to be my tangent vectors, I intended them just to have length 1. Now, again, when we're interested in positive versus negative, it's not as big of a deal, right? But yes, the length of the vector does matter in calculating out how much work is being done. Good. So why don't we do our calculation? So I have my F here, and I want to figure out work. So the problem says, figure out the work done by this force field. According to our definition, the work is equal to the integral of F dot T ds. This is one of the 5 different ways that you could be given do a line integral, right? Do a line integral with a vector field. So like I said, I pretty much convert all of these into F dot R prime of T dt. So this is what I'm going to actually be evaluating out. And so, of course, I can plug in my specific vector field here. So my vector field in our case is x squared comma negative xy. But this is about as far as I can go without having a parameterization. And so now I need to go back into 13.1 world, right? When we were parametrizing curves, and I need to parameterize this quarter circle starting off at 0, 1 and ending at 1, 0. So if I was to do this really quick, we'd have R of t. And if I'm thinking about just parameterizing the circle on its own, I would probably say that my parameterization should be 1 cosine t, comma 1 sine t, because this is a unit circle. It's a circle with a radius of 1. And so I'm thinking about polar coordinates here. And so I'm doing this. Now I don't want the full circle, so I'd probably restrict down. And instead of going from 0 to 2 pi, I'm going to go from 0 to pi over 2. Now this will make sure that I'm on just the quarter circle rather than the full unit circle. My claim here is that, sadly, I'm still not quite right. that this is a wrong parameterization as it stands. Can anyone maybe identify for me what's wrong with this one? Got a guess back here? So yes, it has something to do with, mathematically, we'll call this like the orientation of the curve. So essentially what I've done is that with my parameterization, the classic one, it starts off at 1, 0. And as I increase my time, I'm going to go to 0, 1. So I have parameterized my curve going in this counterclockwise direction. That's the classic parameterization. And yet I wanted to go in a clockwise direction. So clockwise versus counterclockwise will be eventually known in chapter 16 as the orientation of the curve, right? If you're going in a clockwise direction versus a counterclockwise direction. So I have it close to correct, but I'm headed in the wrong direction. I'm going counterclockwise when I ought to be going clockwise. Now, there are a number of ways to do this, but the only kind of wrong one that can sometimes get you into trouble is by allowing your time to run backwards. So that's the only one that I would kind of really resist. In order to get curves like this to change the orientation, there's a number of things that you could do. So for instance, one thing that you could try, maybe in black down here, you could allow one of your values to be negative. So if I did negative cosine of t, sine of t, for instance, we'd have to check our starting and ending points. We have to be careful with that, but this gets it running clockwise rather than counterclockwise. Another reasonable one that you could do would be positive cosine, negative sine. Again, this will get it running in this clockwise direction rather than a counterclockwise direction. Or another thing that you can do that works out well is swapping them. So if I did sine t, cosine t, that works out sometimes well too. So all of these will get it running in a clockwise direction rather than a counterclockwise direction. So to switch to clockwise, consider one of these instead, rather than the classic parameterization runs in the counterclockwise direction. So I'm going to maybe use my last one here, and I'm going to swap these, and I'm going to choose sine of t, comma, cosine of t. And because this is a non-standard parameterization, I want to make sure that my bounds still work here, that I start at the right spot that I'm intending to start at, and I'm ending at the right spot that I'm intending to end at. So let's check really quick, since I've swapped things up. If I plug in 0, where am I on the curve? Where am I on the circle? So if I plug in 0, let's see, I'm going to have sine of 0 is 0, cosine of 0 is 1. So it looks like I am starting off at 0, 1. I'm happy with that, right? I'm supposed to be on this quarter circle, starting off at 0, 1 and ending hopefully at 1, 0. So now I'm dreaming, if all goes well, that when I plug in pi over 2, that I'm ending at the right spot as well. So if I plug in pi over 2, sine of pi over 2 is going to be 1, and cosine of pi over 2 is going to be 0. So yes, I do end at the right spot as well. So this one's nice. I didn't have to change my t values. On some of these other ones, you may have to change your t values. Again, you have to make sure that you're starting and ending at the right spot. So this right here is a parameterization. It runs in the correct direction, runs clockwise rather than counterclockwise. It starts at the right spot, it ends at the right spot. So this is the correct parameterization, or a correct parameterization. There are many. So now that we have a parameterization, we can calculate out the rest of the stuff. So this is going to be my x value. This is going to be my y value for the parameterization. And so instead of x here, I'm going to go ahead and swap out, and x was supposed to be sine. So this is going to be sine squared t. Here we have negative sine, and y was cosine. And now we need a derivative of our parameterization. So the derivative of x sine would be cosine, and the derivative of y, my cosine, would be negative sine. Now that we have this all in terms of t's, and we know our bounds for t, right? We discussed that t should run from 0 to pi over 2 if I want to be on the quarter circle. This right here is the bulk of the hard part of this problem, is really doing the correct setup. From here on out, I mean, we have a dot product, but that's not too bad. So we can evaluate out our dot product. we're going to have what? Sine squared cosine minus a negative, so plus sine squared cosine. And now we have an integral to evaluate. And again, largely these ones they fall back from calculus 1 integrals. So I notice that I have two like terms here. So if you'd like to, you can combine those like terms and just say that this is 2 sine squared t cosine t. So I could erase all this since they're exactly the same. And so I'm going to do another u substitution. If u is equal to sine, then this is going to be the integral of u squared, and du is exactly cosine of t dt. So when I integrate this, I'm going to have 2/3 u cubed. Again, u is supposed to be sine. I'm supposed to evaluate this from 0 to pi over 2. If this ends up being 0, or if this ends up being negative, I know that I've made a mistake somewhere in here, right? Because we just talked about this problem, and visually, we agreed that this ought to be positive. The answer at the end of the day, when I add up all these things, right, we should get a positive answer. And so let's go ahead and finish this up. When I plug in pi over 2 into sine, that's going to be 1, cube that. And then I subtract away when I plug in 0 for sine. Sine of 0 is 0, cube that. So my answer at the end of the day is going to be 2/3, perfectly great positive number. But again, if you did this wrong, by the way, and you use the classic parametrization for a circle rather than this, you would end up with negative 2/3 because you were traveling the wrong way along the curve there. So if you got a negative, this is an indication that's right, something's gone wrong. All right, any questions on this one here? Yes. How do I know the orientation of the curve without having a picture? Well, so if I was just given, right, 210, this one down here, right, I could draw a quick picture. I don't need to know what the vector field looks at all like in order to get the curve stuff, right? So I could just draw this. I know that I'm on the circle. X squared plus y squared equals 1 from 0, 1. So from up here to 1, 0. So the circle, quarter circle, going from 0, 1 to 1, 0, right? I can draw that bit very fast. I don't need to know what the vector field looks like at all. So I agree that the vector field, if I had to draw all this out, that would be a huge pain, right? But still I could get the orientation of the curve or what direction the curve's headed just with these words right here. Any other questions? Well, I'd at least like to set up this last one here. So on this one, we have a couple of line segments. And I have another way of illustrating, hey, do a line integral, right? This is one of the 5 different ways. And what we need to realize here is that the thing next to the dx is the first component, p of our vector field. This is going to be q, and this is going to be r. So if I wanted to rewrite this using my kind of working definition, this would be y, z, x dot r prime of t dt. So my vector field here is y, z, x. Again, the thing next to the dx is the first component, the thing next to the dy is the second component, and the thing next to the dz is the third component. Going back to 12.5, we can parameterize this line segment as what? 1, 4, 5, t plus 2, 0, 0, t ranging from 0 to 1. We can simplify this down into t plus 2, 4t, and 5t. If you kind of combine all this. This then gives you your x component for our parameterization, our y component, and our z component. So these are what we're going to plug in for the y, the z, and the x. This is what I'm going to take the derivative of to find r prime of t. We can see the bounds range from 0 to 1. So we'll get the line the line integral for at least the first part of this curve, C1, and then you can just do the same thing again for C2. So I know it's been a little while since 12.5, so I went through this probably a bit fast, but review your notes from 12.5 on how to find line segments, right? Because this comes up quite a bit, not only on the web work homeworks, you'll see this a decent amount, but I've also seen it on quizzes and exams and stuff like this as well. So, all right, I'll post the full solutions of this one here on D2L, hopefully by 4 o'clock today. So try this one out, and you can compare your answer with what I have on D2L. Otherwise, have a great weekend, and I will see you guys on Monday.